What is the principle of a band gap? It's not straightforward to quickly explain this principle, but I will give it a try. In the upcoming 4 video lectures, I will use a chemical picture to explain the nature of the band gap. You have to realize that I will make some cruel simplifications in explaining the nature of the band gap, so don't tell it your physics and chemistry professors. First, we have to consider the question, how do electrons bound in an atom? As silicon is the most important material for current solar cells, we're going to look how electrons are bound to the nucleus of a silicon atom. Before we will discuss the silicon atom, in this video lecture I'm starting with the most simple atom in our universe, the hydrogen atom. The hydrogen atom has a nucleus consisting of one proton. The proton is positively charged. Around this proton, the much lighter electron is moving in orbits. The electron is negatively charged. This relatively simple system can be described by complex laws of quantum mechanics like the well-known Schrödinger equation. I won't go into detailed physics, but the only thing you have to know at the moment is that quantum mechanics and the Schrödinger equation tells us that in the hydrogen atom the electron can only occupy certain discrete energy positions. The lowest energy position is the ground state, indicated by 1s, and the electron is strongly bound to the proton. It is on average in an orbit close to the nucleus. This energy level is in the so-called first electron shell. If we give the electron more energy, it can be excited to a higher energy level, to the second shell. The electron is less strongly bound to the atom and its average orbit is further from the nucleus. In the second shell we find two types of electronic energy levels, the 2s and the 2p. If we give the electron even more energy, it can be excited to the third shell. The strength of the bond between the nucleus and the electron is further reduced and its average orbit around the nucleus is even further away from the nucleus than the orbits in the second shell. In the third shell, 3 types of electronic states are present. However, in this course, for simplicity, we'll only consider 2 types of electronic energy levels, the 3s and the 3p. Here, the electronic orbital of the electron in the ground state is shown. The orbital reflects the volume in which the electron might be present during its journey around the proton. On the left, you can see the 3-dimensional representation of the orbital, and on the right, we can see the 2-dimensional representation of the orbital. The orbital of the 1s ground state is symmetric in all directions and has the shape of a sphere. The orbital of the excited 2s state is a symmetric sphere as well. However, the sphere is larger, indicating that the electrons are in average orbit at larger distance from the nucleus. The orbital referred to as 2p has a symmetrical shape and in a rough approximation consists out of 2 lobes. Due to the asymmetry, it can be directed in 3 different directions, the x, y and z direction. Consequently, 3 different 2p states exist. We can also go up to the third electron shell in which the orbital corresponding to the 3s is again symmetric and much larger. The electron is less bounded to the nucleus and its average orbit is further away from the nucleus. The 3p orbital is again asymmetric and starts to consist in a rough approximation out of 4 lobes and has 3 different states. These discrete energy levels can help you understand how the periodic table of elements is built up. Before we do that, we have to discuss one important additional property of the electron and one important law of quantum mechanics. The important property of the electron is that electrons can have spins. The important law in quantum mechanics is the Pauli's exclusion principle. First, electrons have spins. What is a spin? Let's consider a charged body in classical electrodynamics like these spheres. We start to rotate these bodies. The rotation of the charge will induce a magnetic dipole. Depending on the rotation clockwise or counterclockwise, the magnetic dipole will point up or will point down. This concept appears to be still valid for a little tiny electron with having the smallest charge possible, the elementary charge. This means that an individual electron can be in two quantum states. Spin up, magnetic dipole pointing up, and spin down, magnetic dipole pointing down. Secondly, I introduced the Pauli's exclusion principle, which tells us that two identical electrons cannot occupy the same quantum state simultaneously. Don't worry about why this is the case just for the moment, except that in nature all electrons obey this law. Now let's consider two electrons with both are in a state with their spins up. Can these electrons both fill the same energy state X? The answer is no, as both electrons have the same spin and they have the same energy. This means we have two identical electrons that occupy the same quantum state, and this violates Pauli's exclusion principle. Now let's consider two electrons which have opposite spins. One spin up and the other one spin down. Can these electrons fill the same energy state X? In this case, the answer is yes. Although the electrons have the same energy state, the electrons are not identical as they have different spins. Pauli's exclusion principle is not violated and these two electrons fill the same energy level. Basically, Pauli's exclusion principle allows every electronic energy level to be filled by at maximum 2 electrons. Using this knowledge, we can now consider the next element in the periodic system, the helium atom, and all other atoms in the periodic table. I will show that in the next video lecture.